Yeah, I'm not muted. There's some open roles. Just DM Nash if you want to do any of these roles. But there's also a Google form. And this is our meeting information. Dice calls is this weekend. We're meeting in person from like 11 a.m. to 7 p.m. at Student Center. We will provide pizza. And there's maybe other CTFs coming up soon. Third and Land, we placed 111th out of like 434 non-zero solve teams. That's not necessarily great, but yeah, there's challenges and info still up, so you can go back and solve them if you want. And if you competed and would like to fill out this form, get your write-up posted on our website. Here's the QR code. And we want your resumes for sponsors to get events for you and help you get a job or internship. It's a win-win. Here's the QR code. There's also the form link in the announcements.
I guess before we get started on the meeting for today, I also just want to mention that Nash will be presenting on the LM CTF Asian project this Thursday, I believe. So if you're interested in learning more about that, and I guess want to see what it's like, what we were doing last semester, and what we're hoping to do this semester, feel free to attend that meeting.
Also, please get signed up on the internal CTF platform. We'll probably be doing some of the challenges today. So Windows has like two types of executables, EXEs and DLLs. They're essentially the same file format. They're just called P file format. Well, in CTFs, we typically see Linux executables of the format named ELF. And these contain headers, like information about the binary, and like sections, which include like pretty important like data that is required to execute the program. If you're interested in looking at the structure, you can use IMEX to view a ELF file, and it'll show you like a lot of like important details to like a ELF file, like the structs and everything like that. But we'll mainly be focusing on sections. So the text section is where your code, your assembly is, and data is where your data is. RO data is just the same thing as data, but read only. Typically it includes only like strings. And BSS is writable. This is where there's global and static variables, but we can also exploit this and write something to the BSS that we want to use for like an exploit later on. There's also these sections, the GOT, which is the global offset table. It includes a table of pointers to resolve addresses, usually libc functions. And libc is mainly just standard functions provided by a library, which just standardizes all the uh, tasks you have to usually do when you're writing a program. At the start, it usually contains invalid addresses. Later, these addresses get converted into like actual addresses, which I'll talk about like later later down in the slide. But there's also the PLT. This PLT contains assembly instructions that jump back into the GOT. So essentially, if we look at the PLT, we'll know like where the GOT of that function is. And during the first call to an entry inside of GOT, a dynamic linker is called. And this dynamic linker resolves the entry's address and updates the GOT entry with the correct resolved address. I'll go more into dynamic linking during like tone because it's quite important to abuse that. And assembly is just code that is stored inside of the text section. It's usually a C that's compiled into assembly. There's two flavors of assembly, which are AT&T and Intel. AT&T has like the syntax of like source, on the left side and a destination on the right. And they use % for registers and $sign for like constants. Well, we usually use this more for like rev and pone and CTFs because it's more easier to read. On the left side, we have destination, and the right side, we have the source like registers. And here's an example. Up top is our AT&T syntax, and down below is the Intel syntax. There's like slight differences, but I prefer the Intel one because it's slightly more readable. So this is what a stack looks like. This is where usually there's local variables and like user data, and also used for like parameters for function calling. A stack usually goes from the high address, which is located at the bottom in this picture, and it goes to a low address, so it grows up. And an important register is the ESP. This is called the stack pointer. This will always point to the top of the stack. We want to use push and pop to remove and add and remove items from the stack. We can also use add and subtract of ESP to allocate or deallocate from the stack. And the base pointer is used when every time a function is called, the base pointer is saved into the stack, and the stack pointer is saved as the new base pointer. This lets us go back to the top of the stack before the function was called. So this allows us to do return back to the original function after we're done calling a function. And we can also use it as a reference to access parameters and local variables on our stack. And a stack frame is just everything between our base pointer and the top of the stack. So for example, this is just one example of a stack frame. And this is basically just a simple hello world with Intel flavor syntax. Here we can see that the first address is push RBP, which pushes the base pointer onto our stack. And then afterwards, we see move RBP RSP, which makes RBP equal to the stack pointer. And the R and the E are just sizes. R is 64-bit and E is 32-bit. And also for the third instruction, we're doing EDI equals .lc0, which we can see at the top points to a string, hello world. And then we call a function called puts. This just prints whatever we gave to the screen. So it's just the same thing as Python's print. And then we move 0 to EAX. EAX is typically the return code. So when we return, that's basically what we see when it returns. And pop RBP basically just restores our base pointer so we can get rid of our entire stack frame, so we don't need it anymore. And then return just returns back to the function plus whatever offset. And these are some resources. For instruction references, we can look at like these two links. These do explain quite a lot about each instruction. And there are different types of instructions and different formats of them. And you can go to the third link to see like a basic stack visualization. And the last link apparently is you can visualize assembly pretty well with it. I haven't used it before, but it apparently is good. Uh, does anyone have any questions?
For when you use puts, like puts only works with the address you have in RDI, or like it can be.
So there is a calling convention, which means that like RDI is used as the first argument, but there are other arguments that I'll go over like next week. But the first like argument is going to be RDI or EDI.
And then like if RDI is the first argument, why was it like RAX? Like the argument for, well,
So are you talking about like here?
yeah,
Also, this one, like when you're looking at a C program, you see at the bottom, it's gonna say return 0, right? Basically, what this is doing here is this is a return register. This is our return value, and then we're storing 0 into it. And then right here, basically this just returns, but now we just have to look at this value to see what our return value actually is.
Okay, so it's like, yeah, the return value. Okay.
Yeah, you recommend the challenges for this group?
Oh yeah. Feel free to ask any more questions. I'll be walking around helping. If you're on Zoom, please DM me on Discord because I probably won't see the chat messages. And these are just some tools to install from 2 weeks ago. These are pretty useful. Please install them. And these are some challenges to try. Feel free to work with each other and raise your hand if you need any more help. Next time we'll go over more low level, like more functions and something like Idian and libraries and basic just debugger stuff. And here's the mentor tracking form. If you help someone, please submit it.